From elementary physics we get to know that matter is built up of molecules and molecules on other hand are built up of minute atoms. Each atom consists of three fundamental particles, namely electron, proton, and neutron. But are these really fundamental? We know that protons and neutrons can further be decomposed into quarks. But what are these quarks? Weird name, isn't it? Let's understand it in this video. My name is Jenna and you're watching The World of Science. At the quantum level, there are a multitude of particles, each with different properties and function. Basically, the particles can be classified into two categories: fermions and bosons. Fermions are the matter-building particles such as electrons, and the bosons are force-carrying particles such as photons and, more famously, the Higgs boson. There is a fundamental difference between fermions and bosons mathematically. Fermions got its name from physicist Enrico Fermi, and they are a collection of particles that follows the Fermi-Dirac statistics. Enrico Fermi and Paul Dirac showed the distribution of particles that follows the Pauli exclusion principle. Given by Wolfgang Pauli, it simply states that no two particles with same quantum properties can occupy same orbital position or quantum states. So if one electron has spin clockwise, then other must have its spin anti-clockwise. The spin is a quantum property of particles that is related to intrinsic angular momentum of the particle rather than actual spinning as the name suggests. Fermions are the particle with half-integer spin, which means mathematically their spin states are represented by 1/2, 3/2, etc. Also, spin states has particular orientation such as upward, downward, or clockwise, and anti-clockwise. An electron has spin value of 1/2, and thus it may exist in two states that are 1/2 up and 1/2 down. Since quantum particles shows their states only in probabilities and thus there are always certain probabilities that both these states can coexist simultaneously. This property is called the superposition principle. The arrangement can be shown mathematically using bracket notations. Fermions are of two types: leptons and hadrons. Leptons are elementary particles and they consist of 6 particles: electron, muon, tau, and 3 neutrino components of these particles: electron neutrino, muon neutrino, and tau neutrino. They all have spin value of 1/2. Hadrons are composite particles that are composed of 2 or more constituent particles. These constituents are called quarks. The term quark was coined by Murray Gell-Mann in 1960s during the formulation of quantum chromodynamics. Gell-Mann proposed a new method inspired by Buddha's Eightfold Path, to organize all the different sets of new particles being discovered in 50s and 60s. He arranged the particles with respect to 2 quantum properties shown as isospin and hypercharge, and proposed the relation between them. He found out that all these heavy particles are behaving like composite particles, forming various series like octet, doublet, and triplet. Components of these particles were named quarks, and they are of 6 types: up quark, down quark, top quark, bottom quark, charm quark, and strange quark. Why were they named like this is a different mystery altogether. But let's focus on hadrons. Protons and neutrons are 2 examples of hadrons. A proton is composed of 2 up quarks and 1 down quark, while a neutron is composed of 1 up quark and 2 down quarks. Each quark has charge values in terms of 1/3 and 2/3. All upper family quarks such as up, top, and charm have 2/3 charge, and the lower family quarks as down, bottom, and strange have 1/3 charge. Let's count. Proton has composition of 2 up quarks and 1 down quark, so total charge will be +1, while the neutron has sequence of 1 up quark and 2 down quarks, so total charge will be 0. I think that's simple and precise. Now let's move to boson part. Bosons are particles responsible for production of forces. There are 4 fundamental forces in nature, and they are electromagnetic force, strong nuclear force, weak nuclear force, and gravitational force. According to quantum field theory, a moving charge creates a changing field in its vicinity and which travels throughout the space and time. Any object that passes through this generated field will feel the effective force. This field is the distortion of the spacetime, and the quantization of the field is by particle known as the quanta of the field. Thus electromagnetic field is propagated through the quanta we know as photon. We can say that two electrons coming toward each feel repulsive force. This is because an electron emits a photon that hits the other electron and pushes it away, and this repulsion is the repulsive electromagnetic force that electron experience. Weak nuclear force is responsible for radioactive decay happening in the material. A neutron which decays into proton can be interpreted as neutron emitting a weak particle, and that weak particle again gets divided into electron and antineutrino. Thus neutron shedding an electron makes it positive, that is a proton. From here we can understand that there must be a weak particle for all three types of interactions: positive, negative and neutral. So there are three weak particles, and they are named as W+, W- and Z0. Strong nuclear force is responsible for binding together nucleons, proton and neutron, inside the nucleus. For strong force, the quantum particle associated is called gluons. Gluons are considered in the framework of quantum chromodynamics. Gluons are exchanged between quarks, and gluons themselves have a quantum property attached known as the color charge. It has nothing to do with the actual color of quarks or gluons. Blame the scientists who named it so. Bosons are the particles that follow Bose-Einstein statistics, that is again a distribution of particles which can occupy same quantum states, thus not following the Pauli exclusion principle. They have spin value of integral, as photon has spin 0, weak bosons and gluons have spin 1. For gravitational force, a new particle called graviton is proposed having spin value of 2, as in relativity, gravity is defined by second-order tensor quantity. But such particles have not been discovered to date and is more analyzed in the field of quantum gravity. Thus Standard Model, while answering all the questions, keep mum on the matter of gravity. Higgs boson is new addition to the Standard Model family, and is the field responsible for giving mass to the elementary particles like electron. The process is not that simple but will be covered in the next videos, as ample time should be devoted for the God particle. Comment down your thoughts about the Standard Model of physics. I hope you enjoyed this video. Do subscribe The World of Science for more such interesting videos.